If 3 to the power of x minus 6 to the power of x is equal to 12x minus 3 by 2 to the power x, find out the value of x. Notice that nothing is specified in the question about the nature of x, so we should consider all possibilities for x, that is, x could be real, imaginary, or complex. With this in mind, let us try to solve the problem. Now 6 to the power of x is equal to 2 multiplied by 3 to the power of x, that is 2 to the power of x multiplied by 3 to the power of x. Similarly, 12 to the power of x is equal to 4 multiplied by 3 whole to the power of x, that is 4 to the power of x multiplied by 3 to the power of x, and since 4 to the power of x can be written as 2 to the power of 2x, we can finally write 12 to the power of x is equal to 2 to the power of 2x multiplied by 3 to the power of x. Similarly, 3 by 2 whole raised to the power of x is 3 to the power of x multiplied by half raised to the power of x is equal to 3x divided by 2x, and that is 3x multiplied by 2 to the power of minus x. Now, therefore, the given equation, that is 3 to the power of x minus 6 to the power of x is equal to 12 to the power of x minus 3 by 2 to the power of x, can be written as 3 to the power of x minus 3 to the power of x multiplied by 2 to the power of x, that is equal to 3 to the power of x multiplied by 2 to the power of 2x minus 3 to the power of x multiplied by 2 to the power of minus x. Bringing all the terms to the left hand side, we get 3 to the power of x minus 3 to the power of 3x multiplied by 2 to the power of x minus 3 to the power of x multiplied by 2 to the power of 2x plus 3 to the power of x multiplied by 2 to the power of minus x is equal to 0. Now taking 3 to the power of x as a common factor, we get 3 to the power of x multiplied by, within bracket, 1 minus 2x minus 2 to the power of 2x plus 2 to the power of minus x is equal to 0. If we multiply both sides of the equation by 2 to the power of x, we get 3 to the power of x multiplied by, within parenthesis, 2 to the power of x minus 2 to the power of 2x minus 2 to the power of 3x plus 1, parenthesis ends, is equal to 0. Let us call it equation 1. Now, since the left hand side of the equation is a product of two terms and the product of two terms is 0, we can write either the first term is 0 or the second term is 0 or both are 0. If 3 to the power of x is 0, let us see what happens. Now we realize that 3 to the power of x can never equal 0 for any real values of x. It approaches 0 asymptotically as x approaches minus infinity, but never reaches never reaches 0, as x can never reach minus infinity. For all other real values, whether positive or negative, 3x is always positive. Therefore, 3 to the power of x is 0 has no real solutions. Let us now examine whether this equation has any complex roots or not. Let us assume that there is a complex root at x is equal to p plus iq, where p and q are real numbers and I is square root of minus 1. Then the equation 3 to the power of x is equal to 0 becomes 3 to the power of p plus iq is equal to 0, or 3 to the power of p multiplied by 3 to the power of iq is equal to 0. Let us call it equation 2. We have seen just now that 3 to the power of p is always positive. Taking natural log of 3 to the power of iq, we get iq natural log of 3. Now inverse this operation by raising iq natural log of 3 as a power of the base of the natural logarithm, that is e, to get e to the power of iq natural log of 3. Thus, 3 to the power of iq is equal to e to the power of iq multiplied by natural log of 3. We know that Euler's formula is e to the power of I theta is equal to cos theta plus I sin theta. In this case, theta is equal to q natural log of 3. Therefore, e to the power of I multiplied by q natural log of 3 is equal to cos q natural log of 3 plus I sin q natural log of 3, and that is equal to cos theta plus I sin theta. Now the right hand side will be 0 only when both the real part and the imaginary part are simultaneously 0. That is, when both cos theta and sin theta are 0. However, both cos theta and sin theta are never 0 simultaneously for any value of theta, or e to the power of I q natural log of 3, or that is same as e to the power of iq, can never be 0. Therefore, 3 to the power of x, which is 3 to the power of p plus 3 to the power of iq, can never be 0. So, 3 to the power of x is equal to 0 has no complex solutions also. Before going any further, please like, subscribe, share and hit the bell so you can be immediately notified for new uploads. It is completely free and only takes a few seconds, and you can always unsubscribe later. Without further ado, let's proceed with the rest of the video. Remember from equation 1 that 3 to the power of x multiplied by within bracket 1 plus 2 to the power of x minus 2 to the power of 2x minus 2 to the power of 3x is equal to 0. Since 3 to the power of x cannot be 0, we have the remaining term within the parenthesis, that is 1 plus 2x minus 2 to the power of 2x minus 2 to the power of 3x is equal to 0. Let us substitute y for 2 to the power of x. Then the equation becomes 1 plus y minus y square minus y cubed is equal to 0, or rearranging terms, y cube plus y square minus y minus 1 is equal to 0. Let us call it equation 2. This being a cubic equation, the general solution is not simple. However, by trying out a few simple values for y, we get if y is equal to 0, then the equation is not satisfied. But if y is equal to plus 1, the left-hand side becomes plus 1, plus 1, minus 1, minus 1, and they add up to 0, and that is equal to the right-hand side. Therefore, y is equal to plus 1 is a solution. Since y is equal to plus 1 is a solution, y minus 1 will divide the left-hand side of the equation, or y minus 1 will be a factor of the left-hand side of the equation. So we can factorize y cubed plus y square minus y minus 1 as y minus 1 multiplied by, within parenthesis, y square plus 2y plus 1. Or by further factorization, we get y cubed plus y square minus y minus 1 is equal to y minus 1 multiplied by y plus 1 whole squared. Thus, the equation can be written as y minus 1 multiplied by y plus 1 whole square is equal to 0. Obviously, y is equal to plus 1 and y is equal to minus 1 are the two roots of the equation. Now, this is a cubic equation and it should normally have three roots, but in this case, two of the roots coincide at y is equal to minus 1 because of the y plus 1 whole square term. Since we had substituted y for 2x, we get 2 to the power of x, that is y, is equal to plus minus 1. Let us call it equation 3. This gives us two cases. Case 1, 2 to the power of x is equal to plus 1, and later we will consider case 2, which is 2 to the power of x is equal to minus 1. Now, since 2 to the power of 0 is 1, if we take natural log of both sides, natural log of 2 to the power of x is equal to natural log of plus 1, and therefore x natural log of 2 is equal to 0, or x is equal to 0 by natural log of 2, and that is also 0. Thus, the equation has a real root at x is equal to 0. Now, consider the term e to the power of x multiplied by log 2, or natural log 2. That can be written as e to the power of natural log 2 whole raised to the power of x. And since e to the power of natural log 2 is 2 itself, we get this term equal to 2 to the power of x. So we get e to the power of x natural log 2 is equal to 2 to the power of x, and in this case we know that 2 to the power of x is equal to 1. So we get the equation e to the power of x natural log of 2 is equal to 1. Let us call it equation 4. Since you are already familiar with Euler's formula, we know that e to the power of I pi I theta is equal to cos theta plus I sin theta. That is, e to the power of I 2 pi k is equal to cos 2 pi k plus I sin 2 pi k. Here we have replaced 2 pi k in place of theta. Now the right hand side, that is cos 2 pi k plus I sin 2 pi k, is 1 plus I multiplied by 0 is equal to 1 for all integral values of k. We know that cos 2 pi is 1, cos 4 pi is 1, cos 6 pi is 1, and like so on. Similarly, sin 2 pi, sin 4 pi, sin 6 pi, etc. are 0. Therefore, e to the power of I multiplied by 2 pi k is equal to 1. Let us call it equation 5. Comparing equation 4 and equation 5, and what is equation 4? Equation 4 was e to the power of x logarithm of 2 is equal to 1, and equation 5 is e to the power of I multiplied by 2 pi k is equal to 1. Therefore, we get e to the power of x logarithm of 2 is equal to e to the power of I 2 pi k, because both are equal to 1. Taking the natural log of both sides, we get x natural log of 2 is equal to I 2 pi k, or x is equal to I 2 pi k divided by natural log of 2, and these are the imaginary solutions for x. Let us call it equation 6. Note here that x is equal to I 2 pi k divided by natural log of 2 will give us many solutions, and each solution will be for one integral value of k. Now consider case B, that is 2 to the power of x is equal to minus 1. Remember, equation 3 was 2 to the power of x was equal to plus minus 1. This equation has no real roots, because for all values of x from minus infinity to plus infinity, the range of 2 to the power of x is from 0 to plus infinity, or 2 to the power of x never becomes negative. However, we can look for imaginary roots using the same step as in case A. Okay. Now, 2 to the power of x is equal to minus 1 implies that e to the power of x natural log of 2 is equal to minus 1. Why? Because 2 to the power of x is equal to e to the power of x natural log of 2. Now, using Euler's formula, e to the power of I multiplied by 2k plus 1 pi is equal to cos 2k plus 1 pi plus I sin 2k plus 1 pi, and cos 2k plus 1 pi is equal to cos pi, and sin 2k plus 1 pi is equal to sin pi. And since cos pi is equal to minus 1 and sin pi is equal to 0, we get e to the power of I multiplied by 2k plus 1 pi is equal to minus 1 for all integral values of k. Therefore, e to the power of x natural log of 2 is equal to minus 1 and minus 1 is equal to e to the power of I multiplied by 2k plus 1 pi. Therefore, x natural log of 2 is equal to I 2k plus 1 pi, or x is equal to I 2k plus 1 pi divided by natural log of 2. These values of x are also imaginary solutions for x. Let us call it equation 7. From equation 6, we get x is equal to 2k pi by natural log of 2, that is even multiples of pi divided by natural log of 2. From equation 7, we get x is equal to I multiplied by 2k plus 1 pi divided by natural log of 2, that is odd multiples of pi divided by natural log of 2. Now combining both these equations, we get x is equal to I n pi divided by logarithm or natural logarithm of 2, where n is any integer, either odd or even. Remember that under case A, we had found a real root of x is equal to 0 also. So, the values of x that satisfy the equation in the question are x is equal to 0, that is one real root, and x is equal to I multiplied by n pi divided by natural log of 2, where n is an integer.